In the vast, unfathomable stretches of the cosmos, there's a mystery that exists beyond the reach of our most sophisticated instruments. It is one of the greatest unsolved questions in modern science. It is invisible, silent, and yet its presence is undeniable. Dark matter, the mysterious substance that makes up approximately 27% of the universe, remains hidden from view. Its existence was first inferred from the gravitational effects it exerts on the matter we can observe, yet no one has ever directly detected it. It has no light, no warmth, no scent, nothing to let us see it directly. And yet, without dark matter, the universe as we know it would not exist. It is the unseen force that binds galaxies together, that guides the evolution of the cosmos, and that holds the very fabric of the universe in place. But what exactly is it? Why is it so elusive? And how do we even begin to understand something we can't see or touch? Today, we embark on a journey to explore the secrets of dark matter, a quest that could reshape our understanding of the universe itself. The universe, vast and teeming with wonders, is a place where galaxies collide, stars are born, and planets form. But amid the beauty and grandeur of this cosmic tapestry lies a crucial element, a form of matter so dominant, yet so hidden, it defies our conventional understanding of physics. We know it's there because we can observe its effects, but what it truly is, what it's made of, remains a mystery. Everything began to shift in our understanding of the cosmos in the 1930s, when Swiss astronomer Fritz Zwicky studied galaxies in the Coma cluster. Zwicky's observations revealed a surprising anomaly. The galaxies within this cluster were moving much faster than expected, based on the amount of visible matter present in the cluster. According to Newton's laws of gravity, the galaxies should have been pulled apart, scattered into space by their high velocity. But instead, they remained bound together. Something unseen was providing the necessary gravitational force to hold these galaxies in place. Zwicky proposed that there must be an invisible substance, which he termed dark matter, exerting its gravitational influence on the galaxies. This hypothesis remained speculative for many years, but in the 1970s, Vera Rubin provided the first compelling evidence for dark matter. While studying the rotation of galaxies, Rubin observed something that confounded the scientific community. The outermost stars and spiral galaxies were moving far too quickly to be explained by the gravitational effects of the visible matter alone. According to the laws of physics, these stars should have been flung out into space, but they weren't. They remained bound within their galaxy, suggesting that an unseen mass was holding them in place. Rubin's groundbreaking work confirmed that the universe contained far more mass than we could see, and it was shaping the structure of the galaxies. Her findings were a turning point, one of those rare moments in science when a mystery that had puzzled astronomers for years was finally beginning to take shape. However, understanding dark matter is not as simple as observing its gravitational effects. To truly comprehend its nature, we must overcome a significant challenge. How do you study something that does not interact with light and doesn't reveal itself through any of the typical methods we use to observe the universe? Detecting dark matter has proven to be an extraordinary challenge. Unlike ordinary matter, which interacts with electromagnetic forces and emits light that we can detect with telescopes, dark matter doesn't interact with light at all. It doesn't reflect, absorb, or emit radiation. It only interacts through gravity and the weak nuclear force. This makes it exceedingly difficult to observe directly. But the search for dark matter is relentless, and researchers are developing increasingly sophisticated technologies to detect its elusive presence. One of the leading candidates for dark matter is a particle known as the WIMP, or weakly interacting massive particle. These hypothetical particles are thought to be massive and stable, and to interact only weakly with ordinary matter through gravity and the weak nuclear force. While WIMPs are invisible to traditional detection methods, scientists have designed special detectors deep underground to shield them from cosmic rays and other sources of interference. In these underground laboratories, such as the LUX Zeppelin experiment in South Dakota, scientists are waiting for the faintest trace of dark matter interacting with normal matter, perhaps a tiny vibration or a flash of light, signals that would confirm the existence of WIMPs. Imagine a particle of dark matter entering a detector, a rare, fleeting interaction with an atom of ordinary matter, causing it to vibrate ever so slightly or release a tiny burst of light. These interactions are incredibly rare, so rare that the most sensitive instruments we have are often unable to detect them. But even a single, successful detection could provide the first direct evidence of dark matter, allowing scientists to study its properties and behavior in ways never before possible. While direct detection remains a tantalizing goal, there are other ways to study dark matter. One such method is through the cosmic microwave background radiation, CMB, the afterglow of the Big Bang. This radiation carries the imprint of the universe as it was about 380,000 years after the Big Bang, providing us with a snapshot of the universe's early days. By analyzing the minute fluctuations in the CMB, scientists can infer the distribution of matter in the early universe. These fluctuations provide indirect evidence of dark matter's gravitational influence on the ordinary matter that existed at the time. By understanding the distribution of dark matter in the early universe, we can learn more about its role in shaping the structure of the cosmos, the formation of galaxies, and the way in which matter began to clump together under the influence of gravity, ultimately giving rise to the galaxies and stars we see today. In fact, dark matter plays an essential role in the very formation of galaxies. Without it, galaxies would never have had the gravitational pull necessary to form in the first place. Dark matter acts as a cosmic scaffolding, drawing together gas and ordinary matter, helping to shape the galaxies and clusters of galaxies that make up the large-scale structure of the universe. It provides the gravitational foundation that allows these structures to form and evolve. Through advanced computer simulations, scientists are able to visualize dark matter as an invisible web stretching across the universe. In these simulations, dark matter acts as the backbone of cosmic structure, an unseen network that guides the formation of galaxies, clusters, and superclusters of galaxies. It's a cosmic skeleton that holds the universe together, shaping everything from the smallest galaxy to the largest cosmic structures. And while we can't see this web directly, its presence is felt in the way galaxies move and interact, revealing its influence across vast expanses of space. To uncover the secrets of dark matter, we are turning to our most powerful tools of exploration. The James Webb Space Telescope, a marvel of engineering and innovation, is poised to help us understand the role of dark matter in the formation of galaxies. With its unparalleled infrared capabilities, Webb will peer deeper into the universe than ever before, studying the earliest galaxies formed after the Big Bang. It will allow us to observe the way dark matter shaped the structure of the universe and give us new insights into its properties. With Webb, we're taking the next giant leap in our search for dark matter's true identity. The search for dark matter is one of the greatest scientific endeavors of our time. Its discovery has the potential to unlock answers to some of the most profound questions about the universe. What is dark matter made of? How does it interact with the forces of nature? And how has it influenced the cosmic evolution of everything we see today? Each breakthrough brings us one step closer to unraveling these mysteries, but the ultimate question remains. Will we ever be able to directly detect dark matter and fully understand its role in the cosmos?